This is part 2 of Lecture 2b for ECE 361, Probability for Engineers at Drexel University, Fall 2016. In part 1, we did some sample problems related to homework 2. Now, in part 2, we'll discuss counting in section 1.6 of the text. The counting principle gives the number of outcomes for a random experiment with R independent stages. The word independent here is important. It means that the options or outcomes in each stage have no effect on one another. You can think of mapping these different outcomes in these stages with a tree. If there are n sub 1 options for stage 1, n sub 2 options for stage 2, and n sub r options for the last stage, stage r, then drawing the tree where each stage represents one of those choices is going to result in a tree with n1 times n2 times nr leaves, and each leaf corresponds to an outcome of this compound experiment. Therefore, the size of the sample space, the number of outcomes in any such compound experiment, is the product of the ni's. Let's give a simple example of the counting principle. In the first lecture, we talked about the basic fact that if I have any finite set, in this case we'll call it omega, and I ask for the power set of that set, the power set is the set whose elements are subsets of the set. And then I can ask for the cardinality of the power set, which is equivalent to asking how many subsets of a given set are there. And we said in the first lecture that if a set has n elements, then its power set has 2 to the n elements. So let's try and prove that using the counting principle. Now we think of omega as having elements omega 1 through omega r, with each of the omegas representing a stage in our compound experiment. And in particular, at each stage, we decide whether or not to include that omega I in our subset. Since there are 2 possible outcomes at each stage, each of the n sub i's is 2. And therefore, when you multiply 2 by itself, in this case r times, you get 2 to the r. We're now going to talk about permutations, combinations, and partitions, starting with permutations. But let's first set the stage. We're going to think in this section as having a fixed set of n distinct objects, and we'll call that set S. The cardinality of S will therefore be n. A key concept in this subsection is to differentiate between ordered and unordered subsets of S. Recall from the first lecture when we said what is a set, that we said a set has 2 properties. The objects in it must be distinct, and the objects are unordered. In that sense, it's probably not proper English to say an ordered set, since a set cannot be ordered. But we'll use this terminology to distinguish a set, meaning an unordered set, and an ordered set, which is more properly called a permutation or a list. Notationally, recall that we use braces to denote an unordered set and parentheses to denote an ordered set. In this section, we're talking about combinations and permutations. Combinations are always associated with unordered set, whereas permutations, described below, are always associated with ordered sets. Let's first talk about combinations. Combinations do not have an order, and therefore the subset of S with elements A and B is the same as the subset of S with elements B and A. As there is no order in the set, these 2 objects are equivalent. However, if we take any subset of S and impose an order on it, then that subset becomes a list. In the special case when the elements of S are numerical, then that list coincides with the traditional notion of a vector. In general, an ordered subset can have repeated elements. For example, A, B, A, with parentheses meaning A in the first position, B in the second, and A in the third, is a valid list, but it would not be a valid set because A is repeated twice. In the special case, when our ordered subset has distinct elements, then it may be called a permutation. For example, parentheses A, B is the 2 permutation where in the first position we place an A, in the second position we place a B. Because order matters, parentheses A, B is a distinct object from parentheses B, A. A K permutation of an N set is an ordered subset R with K elements, S1 through Sk, given positions 1 through K. Here, S1 through Sk are thought of as elements coming from S, the ground set. We want to know how many different possible K permutations can be made from a given N set. And I claim that the answer is the expression given here. The product of n times n minus 1 times n minus 2 all the way down to n minus k minus 1. And the proof is very simple. Recall that we have a set S that has n distinct elements, and we're forming a K permutation, which means we have K positions. We look at the first possible position. There are n possible objects or elements to place in that position. So any permutation that we form is going to have n possibilities for that first place. Whatever we place there in that first position, it's going to leave n minus 1 unplaced elements available for the second position. Repeating this argument at every stage for every position, at the very end there will be n minus quantity k minus 1 unplaced elements for the kth or last position. Recall that in a multi-stage experiment, where we think of the options at each stage unfolding as in a tree, that the number of possible outcomes of that experiment is the product of the number of outcomes at each stage. In this case, n minus 0 times n minus 1 times n minus 2, etc. You may recall that the notation n factorial is by definition the product of n times n minus 1 times n minus 2 all the way down to 1. That is, n factorial is the product of all numbers less than or equal to n. Extending the result from the previous slide to the case where k equals n, we see that what we're doing is we're taking a ground set of n elements, called S, and we're forming all possible n permutations, which is to say every element in S is given a position. The number of ways we can do that is n factorial. Why? Using the same argument as before, we started with n positions in the first, n options for the first position, n minus 1 options for the second position, all the way down until we get to n minus 1, which is of course 1. Multiply these all together, and this is n factorial. So, n factorial is the number of permutations of an n set where every element of the set is given a position. A more concise way of recording the number of permutations is the following. The number of permutations, or ordered subsets, of size k from a set of n distinct objects is the ratio of n factorial over n minus k factorial. And the proof is a simple one line. This is the expression we gave earlier for the number of k permutations from an n set. But if I take this expression and put it up here, and then just keep multiplying by the numbers n minus k minus 1, n minus k minus 2, all the way down to 2 and 1, and then copy those numbers down here into the denominator, then this over this is simply 1, and there's no problem. But now let me look at this numerator in a different way. I have each of the numbers from 1 to n multiplied here, so of course this is n factorial. In the denominator, I have each of the numbers from n minus k down to 1 multiplied together, so this is n minus k factorial. Example. Consider the number of 4-letter words, meaning I don't need actual English words, but rather simply 4 letters from the 26-letter alphabet, consisting of 4 distinct letters. How many such words are there? Well, there are 26 options for the first letter, 25 for the second, 24 for the third, and 23 for the fourth. Next, we'll talk about combinations. Recall, permutations correspond to ordered subsets, and combinations correspond to unordered subsets. For example, if my ground set is the 4-element subset with elements A, B, C, and D, then the set of 12 possible 2 permutations is listed here. Whereas the set of 6 possible 2 combinations is listed here. AB, AC, AD, BC, BD, CD. AB and BA are not distinct 2 combinations. They are distinct 2 permutations. And naturally, there are two permutations associated with every single 2 combination. Equivalently, given any 2 combination, there are 2 orderings of that 2 combination, each corresponding to a distinct 2 permutation. So one question of interest is the number of combinations of size k from a set of n distinct objects. And the key fact is the following. For any given combination of size k, there are k factorial permutations that correspond to the possible orderings of the elements of that combination. In the previous slide, when we looked at the 2 combination, AB, there were 2 factorial, equal to 2, permutations that correspond to the possible orderings, AB and BA. In a 3 combination, A, B, and C, there would be 3 times 2 times 1 equals 6 permutations for that combination, ABC, ACB, BAC, BCA, CAB, CBA. So, recall that there are n factorial over n minus k factorial k permutations, and therefore, and for each one of those, k factorial permutations corresponding to a given combination. Therefore, to obtain the number of k combinations, I'm going to take the number of permutations and divide it by k factorial. That is, the number of k combinations is n factorial over k factorial and n minus k factorial. This quantity corresponds to the number of combinations, or unordered subsets, of size k from a set of n distinct objects. And it's given a special symbol, which we read as n choose k, and which is called the binomial coefficient. And this is its definition. Note, it is not a quotient. There is no division line between n and k. Binomial coefficients have many important properties. We will just cover 2 of the most fundamental. A fundamental identity of binomial coefficients is that if I take the sum over all k from k equals 0 up to n of n choose k, I will get 2 to the n. This is a simple consequence of the binomial theorem, but let's also deduce this same result using some basic logic. We know that there are 2 to the n possible subsets of an n set. And each of those possible subsets has a size, and that size ranges between 0 and n. And we now know that there are n choose k subsets of size k. If I add up the number of subsets, n choose k, over all possible sizes, I should get the total number of subsets, 2 to the n. A second Equally fundamental identity is the following. N choose k is equal to n minus 1 choose k minus 1 plus n minus 1 choose k. To see this, let's look at the following proof. Take any element in that n set. Let's call it E. And then let's consider the collection of all k subsets. All k subsets can be partitioned into two groups. Those k subsets that contain E and those k subsets that don't. For the k subsets that contain E, how many ways can I form such a subset, given that E must be an element in it? Well, if a k subset has a fixed element E, I'm using up one of my slots for that element. I've also taken that element E out of the bag of n elements in the ground set. It follows that there are n minus 1 choose k minus 1 k subsets that contain E. Similarly, consider the k subsets that don't contain E. Since they don't contain E, there are only n minus 1 elements to choose from, and I'm going to choose k of them. As all k subsets either do or do not contain E, if I add up the number of subsets that do have E with those that don't have E, I should get the total number of k subsets. Next, let's talk about partitions. So a combination is a subset. It divides the original n set into two parts, the subset of size k and its complement of size n minus k. Instead of just dividing our original set into two parts, let's now consider a generalization of that idea and divide the set into r parts, where r is going to be a given integer. The natural generalization of the binomial coefficient to this case is called the multinomial coefficient. In particular, given integers n and r additional integers n1 through nr, where those r additional integers must have the property that if you add them all up, you get n, then we can define the number of ways of dividing an n set into r parts, where the r parts have sizes n1 through nr, by the multinomial coefficient n choose n1, n2, nr, defined as follows. The ratio of n factorial over n1 factorial, n2 factorial, and r factorial. Before doing an example, let's consider the special case where r equals 2. If I'm dividing an n set into r equals 2 parts, that's the same as when I was discussing combinations. I'm forming a subset and its complement. Specializing this definition to r equals 2, I see I'm going to recover the definition of the binomial coefficient because I will have n factorial in the numerator, n1 factorial will be k, and n2 factorial must be n minus k. There's two basic combinatorial principles that can be used for which partitions are very useful. The first one is illustrated through this anagrams example. Let's consider the word tattoo. It has 6 letters, 1 A, 2 O's, and 3 T's. I want to know how many different words can be obtained by rearranging those 6 letters. Here, different means that the T's are indistinguishable, as are the O's. So, at first blush, we would think there are 6 factorial permutations of these 6 letters. But I then have to divide by 1 factorial, the number of A's, 2 factorial, the number of O's, and 3 factorial, the number of T's, to eliminate the equivalent orderings for the 6 letters. That gives us 60 possible words from tattoo. A second combinatorial principle for which partitions are useful is this notion of balls and bins. In this example, let's consider the junior class of the ECE department, which we suppose to have size n. And this class is responsible for forming senior design teams in their senior year, and each team is to have size k. Typically here k is 3 or 4. We'll suppose, to keep things simple, that k divides n. That is, n is a multiple of k. If n is a multiple of k, then n over k is the number of teams. For example, if n equals 60 and k equals 4, we will have 15 teams. Then, the number of different ways to form the teams is given by the multinomial coefficient, where I have n students, and each team, which we think of as a bin, is of size k. There's k factorial ways of ordering the students in team 1, k factorial ways of ordering the students in team 2, and there are n choose k teams, each of which has k students, and each of which is independent of its ordering. So I apply the definition of the multinomial coefficient, recognizing I have n choose k factorials in the denominator, so I take k factorial and raise it to the power n choose k. What I didn't yet explain is the presence of this term 1 over n over k factorial. Remember that n over k factorial is the number of teams. In the multinomial coefficient, we assume that the bins are ordered. Bin 1, bin 2, all the way through bin, in this case, n over k. We don't care which students are in which team. We only care that the teams be distinct. And therefore we divide by n over k factorial to eliminate the ordering of the teams. So in the last slide, we just expressed this quantity as the number of distinct ways that n students could form themselves into teams of size k. For example, if n equals 9 students forming teams of size 3, then we'll have 3 separate teams. Then plugging this in gives 280 distinct ways of forming the teams. In this screen capture here from Mathematica, I show the first 50 or so such teams. In particular, each column corresponds to a different partition. Here, students 1, 2, and 3 are in team 1, 4, 5, and 6 are in team 2, 7, 8, and 9 are in team 3. And there are 280 such teams.